Let's implement the Prim's algorithm in Haskell. So the Prim's algorithm, it takes on input some graph and produce its minimal spanning tree. Okay, and I assume that you already know a little bit about it. This algorithm, I will do some short description of this algorithm, how it works. If we take some bipartite graph and in one partition we put one randomly vertex of this graph, and into other partition we put all the vertices except this one which we put in the first partition. If we take the set of cut set edges and extract the minimum edge from this cut set, then this edge will be the part of our searching minimal spanning tree. Okay, and this is the main factor that we need to implement the Prim's algorithm. And it is easy to prove this statement. Let's look at two vertices of our minimum edge of this cut set. So if they connected with this minimum edge, and let's assume that they have the minimum spanning tree, and what if this minimum edge is not contains in this minimum spanning tree? This means that in spanning tree every edge is connected, and also these two edges connected. So this means that there exists some other path from these two edges, and let's look at this path, and let's also put between these edges our minimum edge, and we will have a cycle. And now let's remove the cutting edge from this cut set from this cycle, the not minimum but the other which connects, which contains in our chosen path. And this means that we make our minimum spanning tree is lesser than our initial spanning tree, and so we got to contradiction. So we prove that our minimum edge is presented in our spanning tree. Okay, I will write this proof here in the text in the end of the video, but now let's go to implementation. So we have some function, I will call it Prim. It takes some graph with some nodes of type L and some edges of length L, let's say. And what we have on the output? On the output we have the minimum spanning tree. The spanning tree we can represent the simple list, I think, or we can use set, but for simplicity I will use list here. And we have a list of edges, so we must use this type for edges. Okay, and this is our function definition. Of course, we now to define our function. Okay, we have some graph G, and we now need to implement the body of our function, need to define it. And to define it, I need to use some helper function. I will call it go. This function need to take some current node at which we looking at the current moment. It will need to take some S1 and then S2. S1 is a set which at start contain only one randomly choosable vertex, and S2 is the set that contain all other vertices. And also we need to have the priority queue, I think, and we need to have some result where we contain there we put all our found minimal edges. Okay, so how the algorithm works. We take the first vertex from S1, so we take the current vertex, some current vertex, and take all its adjacent edges, and we put these adjacent edges to our priority queue, and then we select the minimum edge from this priority queue, and then from that edge we select the vertex which presented in S2, and this is the other this is the next current node, and we stop when the have this S2 is empty. So we on every step we take our current node and move it from set 2 to set 1. Okay, and so on our iteration go deep and deep, and at some point then this S2 is empty, this stop. So this is the main description of our algorithm. And I think I need to do some definitions here. We need to define these things. I will start from S1. Okay, S1 will contain some current node. S2 will contain some vertices, other vertices except this current node, and of course we need to define our current node and vertices. So how can I define it? I have the vertices function. So that's how our graph is defined. I already do some intro video about graphs. If you know a little bit about graphs, you can see it where I explain all these definitions. So we have some function vertices that take the graph and reproduce a list of all its vertices. So and I can use this function here to get all the vertices of graph G, and I will receive a list, and I can extract the first element of this list and get the tail of this list. So our first element will be the current element, and the tail of the list will be all other elements except this except this current vertex. So next thing we need to define is our I think priority queue, and to define it we need to use a heap, a binary heap. I already implemented. We have some video. I will put link in this description, but this is an ordinary binary heap. Okay, but with some features. Okay, and now let's we have this import here of this model of the binary heap, and we can use we can initialize our iteration process with empty heap like this, I think. Okay, now I want to define my iteration function. I want to define its type signature first. So with function it takes some current node at first. This is type A. Then it takes some set. So I have this import here of dataset model and the user set, some set of type A. This is the set 1. And also the next argument is some set of also type A, and this is the second set of our cut. So this just disjoint sets. And then we have some list of results. So list of results is represented by this type, the list of edges. And then they need to define some priority queue type. I will use some abstract container for this. Implementation of this container is implemented via CRM of type so this is our binary heap. Actually this is its type, and it has some type integer, I think, and the second argument is our age. So we have the binary heap of the length. The length of our age is represented via, I think not int, via L type. So this is the type of our age length. And this is the heap type. So if you want to understand the details of this thing, please look my video about binary heap. But now you can think about it as an ordinary binary heap, which have some keys of type L and some corresponding to these key nodes of this type. Okay, and what we produce at the end of this iteration process, of course, we produce this result of ages. This is a list of ages of our graph, which represent the minimal spanning tree. So here I put a list and list, and I need to transfer my list to a set, and I can do that the from list function. So both of these values. Okay, what they need to do next? Okay, next thing, I think they can go to our function, our go function definition. So go, it takes some current nodes, some S1, S2, some result, and some priority queue, I think, like this. And here we need to use some some guard, sorry, to define then this top, and this top if our S2 is empty, and we can check this as the null function from the set model. So it returns true, then the set is empty. And in this case we can define our function as a result, so we stop our iteration. But otherwise our iteration continues. Okay, and it continues with some new arguments, with some new data. So we need to define the new current node, we need to define the new set, set 1, and we need to define uset2, so our new partitions. Also we need to provide our new result, and of course we need to provide our new priority queue. Okay, and from this point we can define our these arguments, yes. So the next thing I want to say is that I have this binary heap implementation here, and also I add at this implementation some function. I call it expand. Actually it takes some binary heap, so abstract binary heap, and takes some list of pairs of keys and corresponding nodes, and it add all these key nodes to this binary heap and produce a new binary heap. So we will use this function to expand our binary heaps by new edges which we built from the new cut. So when we get the new cut and every iteration, but by selecting some new current node, then we expand our previous cut with these edges. Okay, so this means that we can define our new priority queue as that they take our old priority queue and expand it with some information. So this must be a list of edges. I will define this edge list a little bit later. Okay, how can I define this edge list? I can define it if I have these two, the set 1 and the set 2. Then I can somehow collect all the edges which have one side in one vertex in set 1 and other vertex in set 2. Okay, and I will call this function is like h2, so it's h2 h2 from s1 to s2. So actually this is our cut set, so we generate it by using our sets and this function. Of course I need to define this function later. Okay, but now of course they need to we also need to define this s1, new s1. We define it by deleting our current node from by adding the current node. So we take s insert, we take this current node and insert it into our s1, and also we must remove our current node from our s2. Okay, now also we need to define our result, our new result. We take some minimum age, and add it to our previous result. So actually this is age that we extract from our minimum binary heap. I think like this. And I think we can define our minimum age. We defined it by using our heap. We extract some minimum number from our heap. Actually not number, we're extracting the age from our priority queue. We take our expanded priority queue here, and let's look at it. This function extract min, so it returns to us the key and the node and new queue. So this means that we need to extract the value from maybe, and after that we will receive the pair, which I want to input match here. Here we have some new priority queue without our minimum age, and we have our age, which represented as some, so we have the pairs, so here also of the key and the node. The key is the length of our age, I think, and the node is actually our age. So this is our minimum age here. From here we can get it from here. This is this type. It has this type, and yes, we defined our minimum age. And next we can go to when we have our minimum age. From this point we can go to definition of the next current node. So next current node, then we name it with this name, and we defined it like so to define next current node we need to extract the vertices from minimum age, and how can we extract these vertices? Actually we can extract they with taking this value and pattern match it with this age type constructor, I think. So we can pattern match it like this. We don't care about length, we only need to know v1 and v2. And how we select the next current node? Okay, I think we can use some guards here, and I need to check if our v1 is a member, if our v1 is member of set 2. If our v1 is member of set 2, this need that they need to use v1. But let's also check the case that our v2, it must be a member of a set 1. Of set 1. Okay, and in this case we can define our current node as v1. Okay, but what if I can take it from here. What if our v2 is member of set 2 and v1 is member of set 1? When we can define our current, we need to define our current node as v2. And otherwise, if otherwise happens, this is that something wrong with our algorithm, and this need that we need to throw an error, but this will never happen in the correctly implemented algorithm. But let's sketch this case, and if this thing happen, this means that we have an error. So, and I will call this error bipartite error. This means that we somehow extract the h from our binary heap, but all the vertices of this h contains only in one part of our graph bipartition. Okay, and that's impossible. And now let's return to our h2 function. So actually I don't need these arguments here, because this is the names defined, already defined in our upper context. Okay. We need to define the h2. H from S1 to S2. And how we define them? To define them, we need to our current node. We need to take the adjacent vertices of our current node, and for this we have this function which takes the graph and current node, I think. Yes. Yes, it's take a graph and no, that's its function. It's type signature. It's a graph and vertex and produce a list of opposite vertices of the edges and lengths. So okay, we take all these opposite edges, vertices, and let's extract them. So this some opposite vertex and the length, I think like this, in this order. Yes, vertex and the length. So here what is the type of this extract length, edges lengths function? What its type? So here we need to provide a list of pairs. So let's look. Expand. It's take a list of pairs of gained nodes, but nodes is the edges. And we go here and let's define type signature here. So I think this is a list of pairs of some type L, I think, and the node is h. I think like this. And this means that they need to build list of such a type here. I built it with list comprehension, and now let's define our element of our list. So we take our list and the not list length as the k, and we take the next argument must be h, and h we can construct with our h constructor, and they need to provide a triple. I think triple consists of vertex, corresponding vertex to our current node, and the length. Okay, and also of course they need to check, we need to use some filter here, they need to check that our corresponding vertex is the member of the set 2. Okay, I think yes. I think yes. And now I forgot one thing. When they chose every new current node, at this moment, and we place it to set 1. At this moment in our binary heap can be some edges which have all the vertices in S1, and they need to remove them from our binary heap. And these edges are created at every step, at every iteration, and we can find them but defined exactly like this, but I will name them to delete. So this is the edges to delete, and these are members of S1. So we take our current node, check all its adjacent vertices, and if somewhere in S1, this means that we need to delete them from our binary heap. And this means that they need to build a new binary heap from this binary heap. So I think it will be named as priority queue, and these 3 signs. I don't know how to pronounce them. Please tell me in the comments. I can't find this name. Okay. And how we define this? To define this, actually we can use the fold function. Fold function with our delete function. In a binary heap I already have the delete function. So let's look at it. It's defined like this. And it's take some node to delete and some container of binary heap. Okay, this means that it can be used with folder. I think let's look at folder type signature. Yes, it can be used as folder, and so we run our folder function with heap delete function. We need to provide initial queue, which defined like this. This is a heap after the deletion extraction, the minimum element, And here we need to provide a list to delete. There they contain all the edges to the delete. So actually I don't need here this pair, I need only the edge. Okay, I don't need a case here. I think like this. Yes, this thing should work. And maybe we can try to compile this thing. Yes. Here of course I need to use this new priority queue to continue our iteration. Yes, let's try to compile. Anyway, I think it has some errors. Okay, let's go to fix them. Parse error on input there. So I forgot otherwise here. Let's take it from here. Okay, reload. As I need to use a dot here, and okay, I need to add for all in type signature for nodes and the length type. Recompile. UTO takes 2 arguments. With the arguments. So actually I think I can just use UTO here like this. And let's define type signature of our UTO h2. So this is the list of pairs of lengths to h. Okay, that's how it needed to expand our priority queue. Let's reload. No instance. Okay, I need to add instances. Here I think I need to add instances to ort A, ort L. I think like this. We can try to recompile and it's done. Thanks. This means that I need this. I can try to run this algorithm. I don't know should it work correctly or not, but let's see. Let's see. Okay, reload, and we have some graph. I can output it here. And what if I run our Prim with this graph? I have some error. So we have errors. I found why this happens. This happens because when I implement binary heap deletion, I assume that n present in the C in our binary heap. But here I have a case then when they deleted something that not in our binary heap, and this means that I need to fix this thing now, and I will fix it later moment. So actually I need to then delete something from a binary heap. I need to first to check that this node is in this binary heap, and I can do this very easy because we have some smart container which allows me to check this for constant time. Sorry, not constant, but with log time. It can be proved with constant time if we move some map to hash map, but this is not matter. I have this abstract function member which takes some node and container and returns me the result. Okay, and here I need to, I think I need to wrap this function like this and define Udel function which take node and container, and I will define it like I need to check if node is a member of some container. So this order, I think, yes, a node and then container. So if the node is a member of this container, this means that they can delete it. This means that they can run this, they can define it as this function, this internal function which actually do the deletion. But otherwise they can stay our container as it is. So this means that I don't do any error reporting about was it actually deleted or not. To do this you need to wrap it to maybe, but I will define it like this. Okay, and let's try to reload. It's done. Go to our heap again, and our Prim is returned to our result. Yes. So what we have, I think it's correct result because I put some great age. But let's redefine our graph in some, I will do it in some form of square, and I put one very big H. So like this, I think A to B with 1, B to C with 2, C to D with 3, and what if I have D to A is 100? So we have some cycle here, and we need to, so this is a square, and we need to, and I think if our algorithm is correct, it must remove this H from the result, so it will produce me this tree. Let's reload and run our Prim. Yes, and you can see that the highest edge is removed. Okay, what if it has, for example, 1? This means that this edge must be removed. Reload and run. Yes, 3 is removed. So I think it works. I don't do any testing. If you found errors, write them in the comments, but actually I can do some other thing here. I can't avoid this deletion. I think I can avoid it by extracting the minimum here, but I need to extract it until I found some edge which have the some vertex which have the vertices in the both of the S1 and S2. Okay. And to implement it, at first I need some function. I need some helper function which ask me a question: is some h is in cut set h or not? So it has some logic like this, I think. Okay, I will call it is cut s. Is cut set, and I need to take some h and pattern match it like this, and now actually I can use this these guards. So here we need to do our checking. So h is represented by two vertices, v1 and v2. If our v2 is member of s2 and v2 is member of s1, we can say that yes, it is a cut set h. In this case, they also can say that this is a cut set h, but otherwise they can say that this is not a cut set h. Okay. Now I think I need some smart extraction function. Smart extraction. Extraction until I found some is cut set h. Okay, I will call it extract minimum until. And how it works? I think we need recursion here. So at first I need to use this thing. So I need to extract min from my priority queue. No, I need some here I need to have some minimum age which as I extracted min age. And I need to check if is this a cut set age. So I check it here. If is minimum, if our extracted minimum age is cut set age, then I can so I need to provide some, I think I need to provide something like this. But otherwise I need to run our, so I need to take priority queue here as the argument, and otherwise I run our priority, so run our recursively our function and do extracting again. So if it's cut set age, then the return the extracted result, but otherwise we run our extraction min with modified, of course, modified queue, and we need to define it. How we defined it? So I need defined it like this, exactly like this. I can define it like this, I think. So we extracting minimum from priority queue, this priority queue which we get on the input, and pattern match it, and if it's not a cut set, then we go deeper to our recursion with a new priority queue which not contain previous minimum, and otherwise we provide this thing. I don't know, need I L here? I think actually I don't need this L here. Okay, and we can remove this thing with new thing. Which defined like this. Yes, I think yes. And of course I can now remove these deletions. This delation I can remove. Let's try to recompile. So some errors. So here I think I need a braces. Not a scope, minimum age. So actually this is our minimum h. And now we have this re-signed PQ here, and they use true signed PQ. Okay. Yes. And now we can try to run this. And I think it's work. It worked for this graph. Let's try for another graph. And for this graph it's also work. So actually this thing I think will be faster than doing the deletion with this method, because we don't try to delete some edges which can be not possible in our queue or not needed to be deleted. We only extract with constant time the minimum until we find some h which is in cut set, in our cut set. One point here, of course I need to use modified PQ. So I extract it here and modify it, and if it is a cut set I use this h and modified q. Otherwise go to recursion with modified q. Yes. Now let's go to our proof, as I said at the start of the video. What are we proving? So if we have bipartition, so we have some bipartite S1 and S2. And if the minimum h, which we want to prove that the minimum h in our bipartition S1 and S2 is in spanning, is in minimum spanning tree. Okay. Bipartite spanning. Okay, fix some errors. And this, with this, the statement, this we need to prove. At first, let's give to our edge the name x, for example, and this x is represented with v1 and v2 and some length. So now assume that they have minimum spanning tree y, sorry. We have minimum spanning tree y, and assume that x is not in y. If it is not in y and they have spanning tree, this means this leads us to that exists path from v1 to v2 and they will name this path as z. Okay. Also, we can say that path z contains some h which is in bipartite S1, S2. I think this h we can mark it with b, some hb, and they can say that we know that b is greater than x. Okay. Okay. Now what we do, we add our x in spanning tree. This means that this leads us to cycle. And now let's break this cycle. Let's break this cycle by removing break cycle by removing b. Okay. And now we have the tree again, and they can say that this tree, we got spanning tree s new s, which is less than our initial spanning tree. Okay. Which leads us to contradiction. And this means that our x, so here we need to say let means spanning tree is y, and they assume that x is not in y, in y. So this contradiction leads us that x is in So here is, I take two names to the spanning tree. Oh, let's mark it with m here, the m here. M here. X is in minimum spanning tree. So they prove that by these steps. Okay, I think I don't do any errors. If you find any errors, please write this in the comments. So guys, I will put this code in the gist, and you can find links in the description. Thanks for watching. Push like button, push subscribe button, and see you later. Bye.